Right, so we have air, which can be assumed to behave as an ideal gas, undergoes a constant pressure process from 1 bar and 27 degrees Celsius to 1 bar and 127 degrees Celsius. And you'll notice that I've already converted the temperatures to Kelvin, so absolute temperature units. So when you're using that ideal gas law, you find yourself multiplying and dividing by temperature. And so you do need to convert it to Kelvin or to absolute temperature units, so degrees Rankine if you were in English units. We want to figure out the change in specific volume, the change in internal energy, and the change in enthalpy. And then they have a little note saying solve it assuming both variable and constant specific heats. So we're going to solve it both ways. So delta U, delta H, we're going to solve it both ways, and we'll see the difference between them and see was it really worth not assuming specific heats were constant. So we will see. We know that if our delta T is relatively small, so here we're looking at only a 100-degree temperature difference, it's probably not going to be that big a difference, right? If you're talking about much larger changes in temperature, then yes, you probably need to actually look up property data. But in this class, if I tell you to assume something or don't assume something, then I want you to solve it a certain way. Okay, so I went ahead. I've got all the relevant tables that I need. So let's just look at those tables and see what information is useful there. Right? So table A1, I have my molar mass here. So that's going to be a useful thing. Um, and let's just leave it at that for now. So the change in specific volume, let's get that guy. So our change in specific volume, and maybe we'll actually solve it. I think we've got room right here. We'll go ahead and solve it right here. Solution. All right. So our change in specific volume, well, it's V2 minus V1. But we're going to define that specific volume in terms of the ideal gas law. They told us what the ideal gas law is. Remember your ideal gas law? It's MRT equals PV, or you can divide both sides by the mass and get things in terms of specific volume, which is what we're going to do. So my specific volume is going to be RT over P, but I'm going to define it at state 2 and state 1. Okay. Remember that R is your specific gas constant. It's specific to whatever substance that you're talking about. So it's going to be defined. And you know what? I think I'm going to, well, before I even get to that, let's notice what things are, how I can simplify this equation already. So my pressure is constant and my specific gas constant is constant. So really, this becomes R over P times T2 minus T1, which is just a delta T. All right, so let's get to that specific volume. Or not the specific volume, the specific gas constant. So your specific gas constant is going to be R bar over your molar mass. I've got a pressure here, and then I've got a delta T here. Well, my specific or my universal gas constant. So this is on your conversion factor sheet. It's at the very bottom. Um, so it's going to be 8.314 kilojoules per kilomole K over your molar mass. Your molar mass is 28.97, and that's going to be kilograms per kilomole. That a bit better. Okay, so remember, we got that molar mass from right here. Okay? We got our universal gas constant from the bottom of your conversion factor sheet in your thermodynamics packet, which is located on your Canvas, the home page of the Canvas page. Okay. Now I need to divide by my pressure. So 1 over 1 bar. And then my change in temperature is T2 minus T1, which you could see is just 100 Kelvin. I'm going to put that right there. All right. So a couple of things that I'll notice are going to cancel out. So I have Kelvin. The Kelvin was on the bottom, right? See, a little bit. Yeah, so it's on the bottom, the denominator of the numerator in that first term. So this Kelvin is going to go away. I've got kilomole, kilomole. And then I'm left with these kind of funny units here, so I do need to be careful here. So I find that it's useful to, I always, if I'm in SI units, I always put that pressure in kilopascals, and my units work out correctly. So we'll show why that is. So 1 bar is 100 kilopascals. Okay, so that takes care of the bar. And then see what a kilopascal is. So a kilopascal is a, well, that's a unit of pressure. It's kilonewton per meter squared. Okay, I got one more to do. So there's a kilopascal, there's a kilopascal. Um, and then let's see, kilonewton. All right, yeah, I'm sorry. It's in my head, getting ahead. I got that kilojoule on the top over here. So yeah, a kilojoule is a kilonewton meter. So let's just see. I got kilojoule, joule, kilonewton, kilonewton. All I've got left are these guys. So that should give me things in terms of meters cubed per kilogram. So I end up getting V2 is 1.148, V1 is 0.861, and so I get a final value of point. It's crazy. Huh. Actually works out to 0.287, which is kind of funny. So 0.287. The reason that's kind of funny, well, I guess no, actually, yeah, it would be 0.287. So the reason is because the reason I was like, oh, that's kind of funny. The universe or the specific gas constant for air, we work with it so much that I kind of got that memorized. It is 0.287 kilojoules. So this is kilojoules per kilogram K, right? And that's if you actually calculate this guy right here. But I guess it makes sense because your delta T is 100 Kelvin. Your pressure is 1 bar or 100 kilopascals. So I guess that works out. Okay, perfect. So we got the first part. Now we need to get our delta U. Well, our delta U is going to be, well, I can look it up. So let's kind of step back for a second. So we're looking for delta U. And the really nice thing for an ideal gas, right? For an ideal gas, we kind of make some assumptions or some simplifications, right? The ideal gas law is one of them. But remember when we used our tables for water, we knew we needed two independent intensive properties to be able to look properties up. Well, for an ideal gas, that's not the case. You really just need one. So if you know temperature, that's enough. If you know enthalpy, that's enough. I guess, how about, yeah. I'll write this. There you go. So it's only a function of temperature. So it's only a function of one property. Okay, so meaning the only thing I need to look up properties is just one of those things. So table A22 has your thermodynamic properties for air. So our T1, remember this is T1, this is T2. So here this would be U2 minus U1. So 286.16 minus 214.07. And the units on here are going to be kilojoules per kilogram. So I end up getting 72.09 kilojoules per kilogram. Now I want you to notice over here, this guy right here. So you have these other columns. So you've got a PR value and a VR value. We are not going to use those. That's not pressure and it's not specific volume. We will eventually use those, but not quite yet. You'll notice that, even up here, they define temperature or they define units for temperature, for enthalpy, for internal energy, and they even give you units for this guy, which we're not going to use yet either. But they give you no units for the relative pressure, what's called the relative pressure and the relative specific volume. So do not use those. The only thing we're going to use are the temperature, enthalpy, and internal energy. I'll also draw your attention to the fact that there are two kind of sets of data. Um, in table A22. So if you scan all the way down, you don't see your temperature, go to the next column and you'll see the other value that you need. Okay. Now we're also supposed to assume specific heats are constant. And best practice, if you're not told what temperature to assume the specific heats are constant at, best practice is to take it at the average temperature of T1 and T2. Don't just pick your favorite temperature, T1 and T2, the average. So average, well, clearly it's 350, right? 350 Kelvin. So I'm going to look in table A20. A20 has, and I'm going to scan up here, table A20 has ideal gas specific heats, well, specific heats of ideal gases. Not all of the gases, but you got 6 of them there. So air being one of them. So there's air, 300, 350, 400. Luckily, they actually have this guy right here. Um, you'll notice this guy, K. This is just a ratio. This is CP over CV. Lots of formulas have the ratio of those specific heats, so this is just tabulating that, right? Kind of like sometimes you see tabulations of U sub FG and H sub FG in your steam tables. Okay, but we're going to use this guy right here. So if you've got an ideal gas, so what are we assuming here? We're assuming ideal gas with constant specific heats. I'll put CV and CP. So our delta U is going to be approximated. Keep on wanting to write CP. CV delta T. All right, what's our CV? Our CV is 0.721. 0.721 kilojoules per kilogram K. And our delta T is going to be T2 minus T1. 400 minus 300, so 100 Kelvin. So this guy ends up being 72.1 kilojoules per kilogram. You'll notice there's really not a huge difference here, and we wouldn't expect there to be because, again, you're looking at a pretty small temperature difference. But we're just kind of going through and making sure that we understand how to solve it both ways. All right, delta H, H2 minus H1. So again, if we're not assuming specific heats are constant, we can look those properties up in A22. So here we go. Going to be 400.98 and 300.19. So 400.98 minus 300.19, I get 100.79. Okay. And then if I assume But I've got an ideal gas with constant specific heats. I'm just going to write CP. Then my delta H is going to be CP delta T. Well, what's the CP I'm going to use? I'm going to use the CP at the average temperature, this guy right here. Right. So it's going to be 1.008 kilojoules per kilogram K times our delta T, which again is also 100 Kelvin. So 100.8 joules per kilogram is what I'm looking at. Perfect. And again, sure don't see much of a difference between calculating it, assuming specific heats or not, right? You can see that very similar. All right. Well, I hope that was helpful. Thank you for watching. Let me know if you have questions.